Okay, recording is rolling. It is Tuesday, November 1st. And today our main focus is going to be these conceptual questions with on energy. We're going to do a Kahoot. Right, so a bunch of guys already logged on. We're a few minutes into class. Right, so remind you guys where we are in the week, big scheme of things. Yesterday I gave you guys this paper, which has a couple of labs on one side. Now we did this one yesterday. This involves the pendulum swinging back and forth. This one we're going to do tomorrow is going to involve those ball launchers that we used for projectile lab back in the day. We're going to essentially do that, but also go one extra step and use this to calculate the spring constant. Okay, so just to plant that idea before tomorrow. Okay. But then on the other side of this paper are these 20 conceptual questions, and these are the questions that you guys are about to see on Kahoot. So if you're following along, that could be a huge help because in a couple days here, I will get you guys your next quiz, and you guys know that a lot of the quiz questions come off these Kahoots. Okay. All right, so yeah, there we go. All right, so with all that, okay, so you switch over here. Say share screen 2. All right, and let's get this thing rolling. Work. Yeah, force times distance. All right, so you guys know that. Here, switch back over here because this could be helpful. You guys remember this 3-page energy table? Okay. And then on the back side, I gave you guys this reference. So this is all the main force of mechanical energy that we're running into so far. Okay. It's the same thing as that poster hanging from the ceiling. Okay. So you guys were just asked this question: what is work? Well, it's force times distance, right? You push or pull something for some distance, as long as they're the vectors line in the same direction, right? So if you're pushing something forward and the distance forward, or if you're lifting something up and the distance is the height, right? So force times distance is the work. Evan and Cole, points on the board. Millie Newton pushes with twice the force for twice the distance. Yeah, 4 times the work? 4 times the work? Yeah, let's switch back over again. Let's see, why would it be 4 times? Well, if you got double the force and also double the distance, what is a factor of 2 times a factor of 2? It'd be 4 times, right? So one particular example of those could be, what if she like lifts a box up like 1 story? Okay, so some weight she's lifting up times some height. But what if she has a box that's twice as heavy and she also lifts it up 2 stories? So not only is the box twice as heavy, but she's also lifting it twice as far, right? Wouldn't that be like 4 times the amount of energy that it takes? Right. So factor 2 times a factor of 2. There you go. All right, Evan extended the lead. What is the unit for work? Yeah, joules. Right? Isn't that the unit for energy? Right. And work is just a transfer of energy. Right? If you push something for some distance, then you're transferring energy, right, to that object. Right? So you guys know that meters represents distance or displacement, that sort of thing. Newtons measures force, which is a push or a pull. Right? Now, if you apply a force for some distance and multiply those 2 together, you can get work or energy transfer, which is measured in joules. Right? Nobody pick watts, but you guys know that watts is a rate of work, like joules per second. Right? All right. Evan's on fire. Your power. Yeah, is work divided by time. Okay. So it's the rate that you're doing work. So this goes back to the notes, like the first, second day that we were doing this, right? So work divided by time. So like energy per time, right? And the unit for that would be, let's see, well, energy is in joules, times in seconds. That'd be like joules per second, also called watts, right? Right? We've got Evan, Cole, Liam, Jack. So what's the unit for power? Yeah, watts, right? So classic example is you see that stamped on a light bulb all the time, right? It might say 40 watts. That means if it's plugged in, turn on, right? It's pulling 40 joules per second. Right? That's what a watt is. All right, Cole's on fire. Evan's in the lead. The amount of potential energy possessed by an elevated object is equal to the work done lifting it. Right, so, okay. So from one perspective, that's the only answer that would check out in terms of the units. Okay. So like distance lifting it would be in meters. The force lifting it would be in some number of newtons. The power, well, that's some number of watts. But work is in joules. And the question is how much potential energy to get something, which is also in joules, right? So that's the only one that matches. Okay. But you know what else? Okay. Let me remind you guys of something really cool here. This goes back to like, it's right near the beginning of our notes when we were doing this about a week ago, is that you can derive one of these in terms of the other. Right? So work in general is force and resistance, but what if you are specifically like lifting an object, right? Like 1 kilogram weighs about 10 newtons, right? Hey, isn't that like M times G to go from mass to weight? Okay? 1 times 10 is 10. Okay? And then if I lift this like 1 meter, so didn't I have to do, see, I had to 10 newtons of lifting force times 1 meter would be like 10 joules of work I did lifting it, which means if I set this on the shelf, then it also has 10 joules of potential energy because it weighs 10 newtons, right? Mg would still be 10 newtons times a height of 1 meter. So do you guys see how mgh is sort of a modified form of F times C, right? If the distance is a height, right? All right, there you go. So the work you do lifting it is equal to the potential energy that it ends up with on the shelf. And if it crashes down to the floor, it's also the kinetic energy of the crash. There you go. Liam, taking the top spot. Points. Kinetic energy equal to what? Yeah, there you go. 1/2 mv squared. So that's straight off that page. Right, we've applied that a bunch of times. So 1/2 mv squared, kinetic energy. M is mass, v is like the speed. Liam's on fire. How much further will a car traveling that speed compare to one of that speed? So if you double the speed, 50 to 100 kilometers an hour, so you double the speed, what happens to the braking distance? Yeah, you guys do remember this. Yeah, 4 times as far. Okay, so this is a really classic physics question. We go definitely review those. That's really awesome if you remember this stuff. If you like double the speed of the car, it's like 4 times the braking distance. All right, so this goes back to, I think I could find your guys' here. Grid 3. Here. Okay, here's you guys. All right, so you guys remember car brake just stop? We talked about this. Okay. Now, if you have an open system consisting of only the car starts off with all kinetic energy 1/2 mv squared. Okay. there's work done by friction that's slowing the car to stop, so it ends up with zero mechanical energy. Okay, so if I do 1/2 mv², so the car has this much kinetic energy to start with. Okay. There's minus the friction force times some stopping distance, and then it ends up with 0 joules of mechanical energy at the end. Okay. There's this interesting relationship between the initial speed of the car and the braking distance. Okay. Like if I take this and I tag it over to the other side, maybe it's a little bit easier to see it that way. Here's the initial. Right, relationship between here. Okay, it's like a square relationship, like a parabolic relationship. So if you double the initial speed, you actually have factor 2 squared is like 4 times the initial kinetic energy. The friction force doesn't change. That factor 4 all gets routed into the distance. Hey, what if you tripled your initial speed? What happens to your braking distance? It's like 9 times, right? 3 squared is like 9. Ooh, right? Good things to know. I've got Liam, Evan, Cole, and Jack. An arrow in a bow has 70 joules of potential energy, maybe like stored in at this bowstring. How much kinetic energy after it's been shot? So there's your conservation of energy, right? Now this is assuming that all the energy in the bowstring goes into the motion of the arrow, right? So if that's true, then there you go. Okay, 70 joules equals 70 joules. So that's setting up a conservation of energy right there. All right, Liam's still on fire, still in first. As a pendulum swings back and forth, like your lab yesterday. Yeah, those are all true statements. At the endpoints, the energy is all potential. There's no speed relative to everything else in the room. Okay? At the lowest point, you could consider all the energy to be kinetic. In fact, that'd be the naturally what we would do, because at the lowest point, you can define potential energy to be 0. And the energy is oscillating back and forth between those types, right? Potential kinetic, potential kinetic, potential kinetic. Okay, as it swings back and forth. All right. So all true statements. Liam's still on fire. Evan in second. When a car's speed triples, what happens to its kinetic energy? Increases 9 times. We just talked about this, right? 1/2 mv squared. Here, just switch my screen over. All right. Let's see. Okay. So, like, here's the car braking to a stop, right? But it's like embedded just in this too, right? Because here's the initial energy of the car. It's all kinetic energy. Okay. Something to do with the speed of the car. But see, like, speed being squared is part of the expression. So if you have 3 times the speed, factor of 3 squared, see, it's gonna be like 9 times the initial kinetic energy. Right? And if you want to continue the story, like braking to a stop, that's going to translate to 9 times the braking distance also. Okay. Right. So the amount of kinetic energy is proportional to the square of the speed. So if that speed changes by some factor, then the kinetic energy increases by that factor squared. 3 squared is 9. All right. So Cole got that one. Oh yeah. One job is done slowly, an identical job is done quickly. Identical job meaning the same amount of work. Those jobs require different amounts of what? Ooh, I got one winner. Who got that? Different amounts of power. All right, so okay, so maybe there's some implications embedded in this question. When it says identical job, percent like the same amount of work, maybe it's like the same force, maybe lifted the same height or something like that, right? So like an equal number of joules, right? Now equal work is like equal energy transfer. So the energy is like the same, right? But if you do one job quickly and one slowly, then suppose you have like this hooked up to a machine, maybe the machine is like lifting a heavy crate or something, right? Yeah, it'd be a different number of watts, right? So you guys know power is work divided by time. So it's the same work, but divided by different time intervals. So the job that's done quickly, you're dividing by a small time interval, which is a huge amount of power. It was like 1,000 watts. It's like, but the job that's done slowly, that's a large time interval. So work divided by time, you're dividing by a large number of seconds. So that might be like, I don't know, like 300 watts or something. It's like, right? So in the end, it's going to be the same amount of work, same amount of energy, but at different rates, got different power outputs, different numbers of watts. All right, who got that? Liam got that. Extended the lead. Which requires more work, lifting 70 kilograms up 2 meters or half that mass up twice the distance? All right, so this is gonna be the same, right? Because now work could be force times distance. Now, the force would be the well, it might be equal to the weight, which is the mass multiplied by gravity field. So I'm looking at like 700 newtons here versus 350 newtons here. Right? But the important thing is the proportions. Like if you have half the mass, then you have half the weight, right? So that's half the force, but also like twice the distance. Right? And work is force times distance. So if you take one of those half and the other double, isn't that a wash? Right? Okay, so there you go. So it's the same amount of work. Right? Or how about the amount of potential energy that you give it, mgh, right? Half the mass, twice the height. Again, it's a wash. So it's the same amount. Right? Half times 2 is just 1. It's the same. All right, Cole, move it up. Got Lehman first. An object that has kinetic energy must also have what? Ooh, all right. I said all right there. All right, so no, we haven't talked about momentum yet, but I defined it for you guys. It's mass times velocity. Right, so that's an upcoming topic. But hey, do you guys see how that's like the same ingredients as the formula for kinetic energy? Kinetic energy is 1/2 mv squared. Momentum is mass times velocity. It's like the same ingredients, right? You just rearrange them different ways, right? Now, you guys know acceleration is a rate change of velocity, which requires a net force. Or so no, you pick that one because kinetic energy, you just have to have a mass and a speed, right? So you don't necessarily have to be speed up or slowing down or changing direction. Okay? And A and C are wrong for the red and the yellow answers are wrong for the same reason, right? So how about this? The Voyager 1 spacecraft, isn't it like just going? Right? It's just going because of inertia, right? Like there's no force keeping it going, right? Just inertia, it's just going, right? So Voyager 1 spacecraft, does it have a mass and a speed and kinetic energy? Yeah, it has all those things, but there's no net force on it. It's just coasting. All right, Liam still in first on fire. We got Cole, Evan, Jack. Oh, a pulley system. Hey, you guys did this as a lab too. What kind of pulley system do? All right. So the best answer is the yellow answer, right? So you can multiply the force. That's called getting a mechanical advantage, right? So back when you guys were rigging up pulley systems, suppose you rigged up like a 3-to-1 mechanical advantage system, and you're trying to lift a 10 Newton weight. You probably only needed about 3.5 or so newtons of pulling force because your strength had been amplified by a factor of 3, right? To lift that very heavy weight. Right? Of course, you can also change the direction. Right? That works too, right? Change the direction with the pulley system. So you can pull down and it moves up, or you can pull sideways and it moves up, right? So, okay. What you cannot do with the pulley system is increase the amount of energy in the system or in the universe, right? That's when applied by the amount of work done. Although, I mean, I guess you can make the argument like, well, what if I couldn't move it at all or something? So, I mean, but if you could amplify the amount of energy, that would, I mean, that would break conservation of energy, right? So that's not going to happen, right? So you can multiply your strength. That's called a mechanical advantage and change the direction. It's fine too. All right. How many joules of work when you're pushing 25 newtons for 3 meters? Yeah, force times distance. Okay, if you have 3/4, do you have 75 cents? Same math going on right here, right? So 25 newtons times 3 meters, get 75 joules, right? How much power to do 40 joules of work in 5 seconds? Yeah, everybody getting it. 8 watts, because you guys know power is work divided by time or energy divided by time, right? Which is like a rate of work or rate of energy. Okay. How about this? Suppose you had an 8-watt bulb. Maybe it's like really efficient right? Kind of bulb, right? So 8 watts, and you run it for 5 seconds. Hasn't it pulled 40 joules of energy off the grid? Right? It's just that problem in reverse, isn't it? It's the same deal. All right, guys, good. I got Leave on Fire. I got Evan Cole Jack. How much work to lift 30 Newton crate 2 meters? Yeah, 60 joules, because force times distance, right? So you're lifting it, moving it up, right, against its own weight. 30 newtons times 2 meters, that's 60 joules. Okay. Also, suppose you set that crate on a shelf. Now, shouldn't it have 60 joules of potential energy, right, compared to where it originally was? All right. How much power to lift 60 Newton crate 10 meters in 2 seconds? Somebody got it. Okay, so why is it 300 watts? Well, power. Isn't power work divided by time? But isn't work force times distance? So you have to combine two things. So I got 600 newtons moving 10 meters. So say the force and the direction is all the same. Like you're lifting up and it's moving up. So isn't that 600 joules? 600 joules of work, right? But then divided by 2 seconds to get the power. So 600 joules divided by 2 seconds, that's how you get 300 watts. Okay? Next go back. 600 joules divided by 2 seconds. Liam extending the lead. Last question for the win. Machine puts out 200 watts of power for every 1,000 watts input. What is the efficiency? Yeah, 20%. So you just divide those two, right? Like suppose you have a machine plugged into the wall, like pulling energy off the grid. So this can be a continual process, right? So it's pulling 1,000 watts out of the grid, right? But maybe it's doing some mechanical operation like lifting an object or something. But you account for that, it's only like 200 watts of output. Right? Now, those other 800 watts, like energy per time, they don't disappear from the universe. They just go into like non-mechanical forms. So it's like maybe waste heat or maybe like sound energy, like vibrating, right? Like things that aren't doing any useful work. So there you go, like 20% efficient. All right, to the podium. The bronze, Cole. The silver, Evan. And the gold, Liam. With 14,000 points. All right. All right, nice job, guys. All right. So. Yeah, if you guys were following along on that page and keeping track of the answers, then that should help you out on that next quiz. All right. Next thing we're going to do here is, let's, you guys remember this packet, right? Okay. So we've done all of these except for one of them. It involves these two asteroids that are gravitating towards each other, right? And I wanted to save this for when we had a few spare minutes, and we definitely do right now. So we're going to go through a few different stories that are related to these asteroids that are gravitationally attracting, right? But this is going to take some deep thinking, right? You guys ready for this?